Good afternoon, and thanks for a kind introduction. It is my honor, a privilege, and a pleasure to be in the beautiful city of São Paulo and in the beautiful country of Brazil. I have been welcomed here in Brazil like a brother, though it's my first time. So, my talk today would be entitled Castballs for Precision Sand Castings. The idea of precision sand is not a term that I made up. It is a term that is conventionally used to describe chemically bonded sand castings and processes primarily used by the automotive industry. So it represents a stronger mold technology. However, the issue of strong indicates a mechanical property for a chemically bonded sand, but what is strong at ambient or room temperature may not necessarily be the case at elevated temperature. And for that reason, I have to describe some of the benefits, the testing, and then the prevention of casting defects relative to these precision sand systems that would prevent us from having these defects. These defects come back to haunt us ultimately in the finishing room, where it drives up the cost for us to do our business. Certainly, I'm representing the Curimbaba group from the standpoint of Castballs. However, this is not a sales pitch. My purpose is to suggest that there are superior materials that needs to be investigated through qualification. What I mean by qualification is a performance predictor. Metal casting, we have molten metal, we have a mold, and we have to fill that mold. In order to make a quality casting, we have to fill quality, we have to mold quality, right? And we have to have a quality alloy. If they don't meet at the mold metal interface, where the metal touches the sand, if there is a reaction, that reaction will give a quality that is deleterious or less than desirable to the outcome. So ultimately, if in the process of mold, melt, and fill, we can provide superior materials, ultimately we will get superior results from our casting. And that's what I want to share today. So, with that, let me advance our slides. This is a rough estimate of the time I'm going to take to discuss why Castball ceramic sand technology, meaning the purpose of it, again, precision sand, and the ideas of control. Prevention of casting defects is where I want to spend the most of my time, and in order to do so, I will be doing a comparative analysis with some new or novel techniques that are adopted by the American Foundry Society, AFS, to show that there can be, in fact, a benefit in using a superior aggregate like Castballs. So, I will start by showing you some data relative to funded research programs by the AFS that started prior to the pandemic period. The granular media that was studied by the AFS are listed here A through G. A would be an example of a granular media that was sintered. So too is B, neither of which is Castballs. None of the materials, in fact, C, D, E, these materials are either natural or fused, and then a natural bauxite material was studied by the AFS, and one of their workhorse silica sands as the control in the experiment. So, here we are showing you the composition of these materials, the sintered materials, the main point I want to make here, these would be medium to low corundum producing materials as a compound, and the others have relatively low levels. The other descriptions, chemically and physically, for the sands are depicted on the screen. I am going to point out some of the pertinent facts. The AFS tried to maintain AFS grain fineness number around 50 to 60 for comparative analysis. Some of the natural materials we couldn't get within those ranges, but this is what an AFS steering committee, a steering committee of experts, required us to use at Western Michigan University in our studies. Here we are showing you the pH values on the system relative to, again, neutral, and then bulk densities of the aggregates, the shapes that are also pictured under 100 times magnification. Those are the important facts about the materials that were studied previously. And again, Castballs was not considered at that time for this study, right? So a new AFS casting surface quality standard was needed. Why I'm saying this is because when we measure the grain fineness at AFS, that just gives us the average particle size. And then the number of screens is a distribution in foundry work that continuously changes as the sand is depreciated and predominantly gets finer. But when that sand gets finer and finer, it ultimately increases a surface area. And surface area, in my opinion, is a major factor driving strength. But strength is only a property of a granular material that we need in metal casting. But what is metal casting? Metal casting is more than mechanics. It's thermal, it's chemical, it's physical. In some cases, it is even more. When the metal touches that sand mold or wall, the reactions are thermochemical, thermomechanical, thermophysical. And for these reasons, we needed to study surface area as well as new technologies that could get us the related properties in the sand. So these are updated techniques where we use optical comparators to check the finish. Surface roughness is a defect. We just don't accept today what comes off the mold metal interface. We have to find something superior that is digital. We are dealing in a world today that is Foundry 4.0. We need to make instantaneous decisions about the level of quality before it leaves our foundry so that we could make the changes, as I suggested before, mold, melt, and fill, so that we are producing quality. So, going forward, there is no relationship between the AFS grain fineness number for as-cast chemically bonded sand. Nothing more than the fact that a finer sand should give us a finer or smoother finish. That's all. But if you have the inappropriate aggregate or the inappropriate bonding agent, we can cause a deleterious circumstance in the process. With respect to the breakdown of sand and how we can compare that, the issue with sand depreciation is the fact that if we compare it as a distribution, the larger particles protect the smaller particles. Or another way of saying it, if I am in a fight, I have to fight in my weight class. I will not be a heavyweight or super heavyweight fighter. I will lose. So to compare these sands, I have to choose the aggregate that is most common. Usually that is the GFN, the grain fineness number. We screen for that, and then we have to compare it in the foundry process by the mechanics that provides the attrition. The two major means of breakdown in a granular media is impact. Bang, 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 and then the rubbing action, that is where. We must look at both of them. Otherwise, we will end up with these sinusoidal depictions of a distribution that tells us nothing. So when we study materials, we have developed at the AFS a pulverizing as well as an abrasive wear test for foundry sands. These particular tests are run at ambient temperatures or room temperatures as well as the elevated temperature test. In the case of this presentation, most of what I will relate to is cast iron temperatures. So we would test these materials in impact and abrasion. Furthermore, we have studied the changes in these ceramic sands. For example, on this slide, I'm showing you one of the sintered sands that I pointed out before compared to another sintered sand. Again, when we look at ambient results, from XRD, we see the level of corundum is still reasonably low. It increases or changes after elevated temperature testing. Still, these levels, even after reclamation, thermal reclamation, cannot increase significantly. This is just some data relative to the pulverizing index that we run at room temperature and elevated temperature. As you see, the materials with the higher levels of corundum perform better. The higher the number in pulverization index means less breakdown in impact and wear. But what if we have a sand that was not a part of that AFS study that contains even higher levels of corundum? Okay, so this particular slide shows where I'll be taking my discussion further. Relative to our work, I am looking at a sand made right here in Brazil, Castball. The chemical composition that will indicate a material of much higher levels of corundum. I've indicated our measurements indicated greater than 80%. This material is more abrasion and impact resistant, and the durability is beneficial to the thermomechanical reclamation of such. For our studies, we looked primarily at an average grain fineness number, about 70, and it shows the surface area, the bulk density, the fusion levels, the neutral pH, and the sphericity and roundness that are very high for this sand that we will compare to the same silica sand that I showed you previously. This picture depicts a modern chemically bonded sand operation that you could find in any foundry producing nation, whether it be the US, whether it be China, whether it be Germany, it could be right here in Brazil. These operations are clean room operations, and they allow us to produce these fancy sandcastles with thin sections as thin as 8 millimeters and produce complex geometries. That's what we get, or that's what we need from precision sand casting technologies using chemically bonded sands today. So, some background. The requirements for these precision sand systems for chemically bonded sands, and I'll mention their names right now. Certainly the 3D printing technologies for additive manufacturing, and then the more conventional systems, the hot box systems, such as Shell, the cold box systems, the urethane-based systems, and the no-bake systems, typically for our larger chemically bonded sand casting processes. Okay? But they today are running in some cases without the touch of human hands. But where does the magic in the casting process happen? For us at the AFS, we have a research committee called the MMIR, The MMIR stands for the Mold Metal Reactions Interfacial Committee, and I serve on that committee as a researcher. And I'm here to tell you, we have seen even fine, smooth grain finishes with deleterious or rough surfaces bearing defects such as veins and penetrations that we literally have to spend a lot of money and a lot of time, time is money, in the finishing room to remove. So we have to study where that magic happens. The AFS has many tests currently on the books, but only a few of them are for chemically bonded sand systems. So we get very little information from the chemically bonded sand standards. A performance predicting measure for precision sand systems is needed. That performance predicting measure is something that I will be describing today. It's a casting trial based on the properties of the chemically bonded sands that we get from the laboratory. What are the conundrums? What are the confusions then that we get with chemically bonded sand processing? Where do the does the numbers mean? It means very little if there is not livable variability. Livable variability is relative, but it still has to be low. The variability must come only from the process. It cannot come from the sample, it cannot come from time, and it cannot come from our testing. The variability that we have to measure against quality is the variability of our process. And that we have to determine ourselves within the foundry in terms of what is livable for us. Livable means what my customer is willing to accept. That's what it means. Another conundrum is what we should be measuring. I believe these should be dynamic properties. The dynamic properties are properties happening in near real time from the metal casting process that gives us engineering property data that is thermomechanical, thermochemical, physiochemical, etc. When should we measure? Should we be measuring hourly, daily, weekly? I am suggesting we need to be getting this data at line speed. We need to be getting smart data. Smart data is not just digital data. It has to be coming from the process in near real time. We can't use yesterday's data. Yesterday's data about our foundry systems is legacy. It's not going to help us with the changes in our environment, with our materials that are today. And we need to be responsive for these casting defects in the foundry and before they leave our foundry to cost us warranty or guarantee complaints. Where should we measure? Again, I've mentioned this before, but I'll say it again. In the process at the mold metal interface. Why? Because that's where the magic happens. The purpose for precision sand testing is a quality process control program that we are looking for in the foundry, something that we need data for that allows us to tell us what the next casting will look like. We want to predict when a defect or shift might happen, and we need the data to do so. Casting defects, the characteristics of the chemically bonded sands are altered from what we produce at room temperature to what sees elevated temperatures at the mold metal interface. Certainly, the quest for consistency. What the quest for consistency is simply the idea of us producing the same level of output with the same center, the same amount of livable variability, and the same distribution for that process. 8 a.m. when we start work, 9 a.m., 10 a.m., and so on and so forth throughout the day. Technology and sustainability is crucial to our world. We live in a green country. You live in a green country here in Brazil. We want to keep it that way. And certainly we want the foundry industry as well. So it has to find a symbiotic relationship. New materials like Castballs has to be studied with this purpose for a beneficial reuse and a sustainable end to our manufacturing. Other materials that are ceramic based that are in conjunction would be coatings, sleeves, filters, or other blends of sands, binders, and internal additives. Typically, what I mean by that, there are external additives like refractory coatings, but today there are people selling you all sorts of magic compounds that you can mix in with the sand. In my opinion, we have to question whether that benefits us the next time we use that sand. So, we have to consider the input boundary conditions for solidification simulations. Here at the conference, I saw good papers relative to that technology. Most foundries use the models of simulation, but simulations is a model. I believe all models are wrong. It is a mathematical representation of what is reality. It's not reality. Testing is reality. But nobody makes money from testing. But testing gives us the data. We need the right data from our materials. And this is why we need initial tests about the materials that we use. And if we can get that data, we can use that data that is missing right now from simulation solidification. Certainly, the simulation solidification excels with the metallurgical properties, but what is missing is data about our sand binder systems. And for that reason, that model is wrong. But models like simulations are useful. But ultimately, my purpose today is also to save you some time and money, because if we get enough, or what I'll call big data, from our processes that are in control, we can stop testing. I'm not ready to stop testing today, but when we have that, we will be able to. The technological implications for chemically bonded sands is cost. That's what I'm pointing out here. Excuse me, let me go back. We have rapid mold developments for precision sands in our automotive industry. For precision sand, and SPM is the acronym for semi-permanent mold. That's where we are putting a sand core into a metal die to produce a casting, something like a sport rim. Those processes are running today, at least in Michigan, at 60 molds per hour. That's where I'm getting this data from. Alternative molding media that we're using in the industry, as I mentioned, the conventional processes, again, hot box, no bake, cool box, and in some countries, they are literally injection molding cores at very high speeds, much higher than 60 per unit time. And then 3D printing technology is gaining some market share, some larger market share relative to the conventional processes. So we need to know what's going on with them. The traditional casting trials that we run in our foundry, it takes a lot of material, a lot of time, and it's costly to do. Can there be a simpler model to give us the answer to qualify our sand binder systems relative to the alloys that we use, not only for temperature, but for the chemistry as well as the metallostatic head pressures that we use? So the baseman and the step cone that were once standards are now replaced by technologies that I will show you today. The qualification strategy for chemically bonded sand, molds, and cores follow this type of analogy where we can say, where mold 1 can be the same as mole 2, it can be the same as mole 3, and it can be the same as the nth mole. But today, with technologies like 3D printing for chemically bonded sands, these molds and molding materials does not have to be the same mold 1 to mold 2 to mold 3, or it can change to the nth mold. But we still will need the data at line speed. So the questions that we have to ask are, does the sand dish-shaped specimen, the sand dish-shaped specimen is an AFS specimen that is 50 millimeters in diameter, and the thickness is 8 millimeters. And that's why we describe that dish-shaped specimen that is a standard at the American Foundry Society as a cookie. Hopefully you like cookies, because you're going to hear the word cookie a lot today. So we are using the cookie substrate to represent the mold and core. We want to know if it will vary, meaning change, mold to mold, core to core. Does the sand dish-shaped specimen vary castings to castings? Where do we get the cookie from? We get the cookie when we make that core or mold. We have that in our tool. We produce that when we 3D print. So I am saying no to the dog bone. We don't eat dog bones. Cookies are better. And I'm saying no to the Kit Kat bar. It's not that they are bad specimens, but with these specimen types, we only get mechanical properties. What I want to show you is that with the cookie, which is a simple shape, we cannot reinvent the wheel. We don't reinvent the wheel. We get shape factor advantage. If I put heat at the bullseye, right at the center of the cookie, I know where that heat will go radially or axially in that cookie. But if I have a sexy shape like the dog bone and I put heat or stress on that, it is non-uniform. Similarly with the Kit Kat bar. But the most important point is that in the complex shape, we could have stresses due to the ejection of the specimen from the tooling. That shows up as stress on the casting. Similarly, with heat transfer, as I mentioned, with the simple geometry, we can model that more effectively to get the appropriate data. There was a paper that I did some years ago at the World Foundry Congress in Incheon, Seoul, Korea, and there's a technical paper that shows why there is more consistency, or in a simple sense, less variability for chemically bonded sands using data from the cookie. Today, I will show you the tests that we use to gather data from cookies. Again, the specimens must be representative, meaning it has to come from the process, and if we can, let's get that data today when we are making castings in the process. So for the shell process, shell is a hot box process. I am going to have a back. This will be a video that shows you how we use the shell hot box process to make a cookie. By the way, I want to acknowledge all the sand testing equipment developed at WMU. This was with the kind and generous research support by Shinto Kogyo, Japan. You will see their name on our equipment. This is an aeration shell process that we blow on the low pressure. With low pressure aeration technologies, you make a much tougher shell core than by gravity or high pressure air. So this would be an example to represent now the substrate for shell. Okay. Next, I want to mention how we use this process in industry. We take the recommendation from the binder supplier. They suggest if we are aluminum, if we're iron, if we're steel foundry, what we should be making our cores at. I don't necessarily subscribe or believe that, but at the end of the day, the process benefits are, again, for precision sands, superior finishes. Again, what we want to look at here in finishing are the lower the numbers, the better that surface finish. And then another consideration, the only other property we get are hot strength values and the tolerances for non-ferrous castings. Sorry, I gave you inches here. I will convert that to metric a little bit later. But again, we are always looking for tighter and tighter dimensional tolerances on these processes. Okay. One of the major problems with shell is that it needs visual acuity. We have to use our eyes. And when we cure the shell sand, this depiction is saying my cookie is severely undercured. This cookie is severely overcured. Maybe in the undercured cookie, it may lead to gas-related problems. In the overcured cookie, it is a friable issue, and this khaki tan color is perfectly cured. Now, that's what I might be seeing with my eyes. If you have better than 20/20 vision, you might be seeing a different color. We know we don't always see that the same. But now, what if that sand, an opaque sand? We do not know when we are cured. So this is why we need qualification techniques around this chemically bonded sand process, and we'll show you how we establish the optimal conditions for this process in cure. Okay. Next process is the cold box process, and this is showing you some tooling. This is a 3-piece tooling, but it can be more. To give you some ideas, we have to vent this tool around the parting line, and then some simulation for blowing the cold box system. We can predict the density from simulation and look at the blow pressures through gassing those cores, and then the curing and curing front progressions as we purge the catalyzing gases through this system. Okay. Ultimately, we will produce our cookie cores. This would be an example of such, and how we make the specimen tree on the phenolic urethane cold box specimen and tooling. However, there are many foundry customers in the US or other places that have made their own tooling. This is a video. No, back. Video. Yeah. Right. This will show just a simple tool that they are producing the cold box specimens in that process. Okay, and you see. Next. Next. Okay, this is a video as well. This is the no-bake pep set process. In this particular case, the tooling is even simpler. The operator, at the time they are making their cores and molds, they can take a sample of sand and just strike it off. This is, again, a very simple approach to producing the cookie specimen. But ultimately, whatever the process, hot box, cool box, no bake, we can also try blends in the system. Here is systems with 100% silica sand. Here is maybe 100% chromite. Here is 50-50. Here is 80% silica sand, 20% chromite. Here is 80% chromite, 20% silica, and you can see 40-60, 60-40, any blend you want to try. For heat transfer purposes, what is the benefit, or maybe you want to consider reducing the cost of your aggregate. We can try that. With 3D printing technologies, I showed yesterday in a presentation, we have a model, and that model is a dodecahedron. It allows us to produce 13 specimens, 12 of them on the faces of the dodecahedron, and one that we randomly print in the center of the model. This is the cookie cage. The cookie cage allows us to ascribe the position in the bill box, the height, the orientation, the print direction, so we can understand how these may cause variation in the metal casting process. These are the actual cages. This is the one cleaned up after the archaeological dig, so to speak. But after we have our specimens from our various chemically bonded sand processes, we are ready to get data. Data that we have these AFS tests. These AFS tests are now documented in the AFS Mold and Core Handbook circa July 2018. So they are in the 2020 edition of the AFS's Mold and Core Standardized Testing Procedure Manual. We have a thermomechanical test. This is the preeminent test for cookie testing, the thermal distortion test, also known as TDT. We have a hot permeability test. The reason that we run the permeability test hot is because at ambient, the permeability is only telling us how fine or coarse our sand grains are. But when, again, the metal meets the mold or the heat touches the cookie, we now see either a condensation layer or a gelatinized layer blocking the interstitials of the sand grain that will reduce the venting characteristics or the permeability of the sand. We have 5-minute techniques, meaning in 5 minutes we can get the total organics, the volatile chemicals, as well as the moisture measured in your specimens, and to characterize the impact strength of the cookie at room temperature. This particular test can tell us the strength of our mold and cores. Why we look at impact for toughness is because in shakeout, we need impact energy, and the impact energy after the retained strength will give us the amount of joules required for shakeout if needed for that mold or core. The abrasion test is a test representing the friable losses or the level of cure on the sand. It is indicating, it is indicative of an operator rubbing his or her hands on the sand mold. And if there are erosive losses, we know where that sand ends up. If the molten metal flows in the mold, it ultimately can end up in the pattern cavity. Okay, so some more information individually about these testing. The LOI test is the loss on ignition. The AFS test typically takes 3 hours, 2 hours at 1000 degrees C, and then we have to cool that specimen off before we can take the weight again. And the thermogravimetric measurement indicates the LOI. That is too long. That particular test, if we are waiting 3 hours for that data, and there is a hydraulic line leak on our sand or so, and the organics go up in our sand, we are making casting defects as fast as we are making molds. So the technologies developed at Western, again, our major funding agency, as you see here, would be Sinto. They have automated this technology, and they have this equipment available in Japan for fast LOI testing. In more recent times, just this year, at Western Michigan University, we have modified this technology so that we can measure the organic compounds as well as moisture all within the same time period of 5 minutes. So again, I will forego the explanation of the computer data acquisition, but what is happening, we ramp up to the AFS standard test temperature and we look for that data to flatline before we change and check the mass again to ramp up the temperature to measure the VOCs and then the LY. So we check moisture. The moisture indicates dry sand. We move and we measure the VOCs, and then we measure the total organics of the sand system. And again, this today can be achieved in 5 minutes as an AFS standard. The permeability is a long and drawn out formula that the AFS gives a number that is a complex measurement that literally tells us very little. It only tells us how fine or coarse the sand would be, because this test is standard runs at ambient. So it forces 2000 centimeter cube of air through the specimen, and the time ultimately that it takes for that to happen is the permeability number. I will show in a video how we run this test using the MQI modified. Can we play the video? It's okay, we can play this one. Go ahead. It's the same idea. So the specimen is gasketed and it's placed in a tube. This is the laboratory test. We are working to automate this technology as well. And again, we are looking at what is 2000 centimeter cube of air going through that cookie. That will generate the permeability number according to AFS. But then we will use the MQI test, which is a mole quality index standard, based on a pressure of air and the resistance to the pressure of that air from traveling through the specimen, that we get a direct number. What we have done, we have collected this data to find that there is an inverse relationship between permeability and the MQI values. And this now will allow us to measure more important characteristics of the sand that we could use as property data, such as Darcy's numbers. But what is more important about the permeability is the fact that we can do it hot. And with hot permeability, we will get an indication of how the venting characteristics drop at the mold metal interface. Can you play the video on this? This is the disc transverse strength test. This transverse strength, we don't place a lot of importance on this, but it does give us the mechanics. Why I say we don't place importance is because not too many cores or molds fail in compressive shear. More of it is impact. So we prefer using this technique to show how we get the energetics to break that cookie before heating and after heating. Before versus after will give us an indication of whether that core in the mold will shake out. And the reason for this is if we are shaking out all day, we're not making any money. It's a productivity issue. Okay. We have automated this test as well. So this could be inline. This is a video, but I'm going to skip this over for the sake of time, just to show, just to move us along. This is the abrasion test. This is the one that tells us about the level of cure in the sand or the friability of the chemical binder system. It's a ceramic ball that is 4 millimeters rotating against the specimen at a predetermined load for 20 rotations. And we look at either the depth of penetration or the losses of sand as a percent. That is the function of the friable losses from abrasion. It's representing the molten metal flowing past the chemically bonded sand. So from this data, from these tests, we get data, but the preeminent test for thermomechanical testing is the thermal distortion test. The expansion, contraction, and degradation experienced by the molar core under the extreme heat and liquidus pressure of the molten metal. What this means is that in our casting process, certainly we as foundry people, we like to think of temperature. But it's not just temperature, temperature, temperature. Equally stressing in the casting process is the liquid metal pressure that is measured by rho GH, and as it presses against the mold wall, it is the opportunity to cause deleterious conditions such as veining or crack propagations. So here is a scanning electron microscopic shot, or SEM. I have tracked this particular crack on this SEM that occurred on this cookie, and if we note this location on the sand grain at lower magnification to higher magnification, you see the binder bridge. And this particular crack opening now is about 2 millimeters. If we wet that with molten metal, that particular expansion, could cause oversizing of the casting, but the distortion issues related to that crack can be penetration, vein, rat tail defect in the casting. So this is what a rat tail would look like, a fin. That's what we may need to grind off in the finishing room or do some grinding or machining on these surfaces to improve the surface quality. So how the thermal distortion test works is that we can support the specimens circumferentially 1 millimeter around the circumference, and that periphery is held on a gimbal to self-align and self-center the cookie against the hot surface that is 20 millimeters in diameter. The test duration is depicted through simulation analysis of the casting. Typically, high head pressure castings take a longer time to solidify, but that is important in this process. And our test temperatures, we can go up to 1450 degrees C if we are representing iron. In this case, we were looking at a copper-based alloy, so the test conditions were closer to 1000 degrees C, or if it was an aluminum alloy, we would look at head pressure against an aluminum temperature like 700 to 760 degrees C. And this is how our mechanics or thermomechanics would relate. To show you this in a cross-sectional view, the neutral axis is not what is important, it's the rotational axis of where is the cookie hot surface interface that would represent the mold metal interface in casting, and we're delivering the head pressure against that. So if the cookie is moving away from the hot surface, that would represent pure expansion, a curve moving up. If the cookie sags around the hot surface, it would result in plastic deformation, up and then downward movement. So there's a video here to show you. Okay, so the cookie is loaded on a gimbal and it's brought in direct symmetrical contact to the hot surface. That is the alloy temperature superheat, and we are tracking the temperature on the back side and at the hot surface. The cookie is nominally 50 millimeters in diameter, so we could track in real time its movement radially as well as axially. So what we are trying to do is get data 3D for temperature and dimension of the cookie in this test. The cookie does remain intact so that we could evidence additional data through observations using a macroscope, a 3D macroscope, to get surface roughness data, to get volumetric change data, and to get loss data relative to sand. So this is what the specimen will look like before the test. This is the heat affected zone, the HAZ, or heat affected zone, where you literally are burning out the binder systems. When that binder system is blown away, you could see where at one time there would be a vein or crack in the system, and that hairline crack on the backside. That we could indicate, and we know when that's happening. How we know when that's happening? We have data from a thermal distortion curve. So here I'm showing you, for example, 4 different sand binder systems. The sand is the same size and distribution in all cases. It's the same sand, but we're using a shell hot box system, a urethane cold box system, a furan system similar to what is being used in 3D printed, and an alkylate isocyanate oil that would be more common in no-bake systems. And the percent binder is held constant for each. The only reason that we're keeping the binder system constant here is so that we do not indict any chemistry. And what we see from that control experiment about the origin, the vertical axis shows the displacement or distortion, and this is time as a function of temperature. So we are testing at a steady state, and we are looking where then will that casting solidify. We don't want too much movement, nor do we want cracking. But what we see is that the thermal distortion test can distinguish between the different systems because of a thermomechanical signature relative to a percent binder being held constant as well as the sand. So that we know that the issue of distortion is more a cause of the chemistry rather than anything else. And if there is a crack propagation during the test, it is indicated by an inflection point. So we know how long it takes for that crack to develop. If the sand binder system cracks and there is liquidus in the metal, that's where we get a vein, that's where we could get penetration. But if the crack occurs much later in the test and the iron has skinned over or solidified, then we don't have to worry. That crack will help us shake out. So we have evidence, we measure that crack propagation relative to the heat affected zone, right? Again, there are other additives, as I mentioned, engineered additives that we can place into the recipe. Again, the cookie is nothing more than a substrate to allow us to study whether our refractory coatings are insulative, chilling. Are they preventing the defects we want them to prevent, or am I better off using a superior sand binder system? So these coatings are used to prevent these expansion defects, as I've shown, gas defects, and erosion defects such as inclusion and spalling. What spalling is the idea of that heat transfer due to radiation, not convection nor conduction, but radiation that hits the ceiling of the mold, and sand falls away, and then later metal touches that to leave an uneven or rough surface. That's what a spalling defect is. And I know you know what inclusions are. But here, these defects are rendered on this rotor or this impeller, propeller, that is shown here. And we are looking at, does the refractory coating technology provide a marginal benefit to alternative molding media? That alternative media, if we're using a ceramic sand, a more expensive sand as opposed to silica sand, does that really give us a benefit? Because to put a coating on, it's like putting a Band-Aid. Does the Band-Aid heal the cut? Or could the cut heal without the need for a Band-Aid? But we have to pay for that Band-Aid, And in this case, we have to dry that coating. It takes time and energy. So again, we are looking for superior aggregates. This video. So this is how we would study the coating effects, because the coating effects for rheological characteristics of a coating, it's a function of dip time. And every, sorry to be sexist, but there is only men here. Every man shakes differently. So in this case, we have to allow that to be controlled, the wetting and the leveling of the refractory coating to control the level and depth of penetration. We study from the coatings the percent solids, surface tension issues by contact angle measurements. That gives us this data. If you're interested in rheological controls for coatings, there's a paper that I was produced and published at the AFS circa 2010 at the AFS. So all of this type of data relative to contact angles, here is a fine sand, here is a coarse sand, and the related rheological properties such as shear, they can be documented well. But we do know if you use the coating the wrong way, the coating changes 8 a.m., 9 a.m., 10 a.m. You can't blame the sand binder system for that. You have to control your coating separate for that. So the question as well is the proud coating layer. The proud coating is how much coating above the nominal level of the cookie, or how much is needed for mechanical interlock subsurface penetrated layer. That subsurface penetrated layer and the proud layer can affect the insulative as well as the chilling behavior of the refractory coating technology, as well as permeability. So here is the nominal level for coating, no proud layer, everything below the nominal level, and with coating we can see that it affects the permeability. So permeability increasing with less coating, we literally can use permeability data to tell us how much coating is there. Okay? It is a direct relationship. We have measured that. So here are specimens cookies, uncoated. These are naked cookies after thermal distortion, and the back side of the specimen. Again, the pyrolysis, this black layer, we can measure how much organics is left. And there is significant. There is 40 to 60% of an organic binder there. It's not gone. This is with the coated. This is a micrographite coating. This is the heat affected zone. There is a fine crack. But on the back side, you can see that that particular coating is protecting that loss of sand relative to that situation. The video here, please. So I will use low pressure, 0.003 megapascal, something like that, low pressure to blow that coating away. And there is where we're showing you those pyrolyzed regions. So when we study the cookie with 38% solids in the coating, you see that it is remaining intact. So less coating can be more. What is happening here with a significantly proud layer, gas development under here, under this layer, under the layer of coating that is proud, is causing delamination and distortion to that sand binder system at 42% solids. So the question is, does the coating work? And what we are looked at, again, this is for a specific coating, micrographite. Uncoated in blue, 42% solid, a lot of coating to low coating levels. The coatings, in this case, as a chill coating, is not preventing distortion. Here is the origin. This is expansion. After 20 seconds, there is plastic movement of the cookie. Starts to move. So we have to engineer the sand binder system with the cookie to prevent that coating. With ceramic sands, we have seen, and I've shown yesterday in work, that the ceramic sand materials are thermally stable and they literally hug that origin line. It's expansion and then plastic deformation, and this is how we track the distortion. But the foundry engineers are never satisfied with laboratory data. All that I've mentioned is property data that we need to feed our simulation models. And now we have developed casting trials. Can you play the video on the left? Next, back. Yeah, this one. This is the one that we use for studying erosion. So there are cookies under this head. We deliver that metal at a turbulent fill. We want to achieve half a meter per second because we have data to show that at that velocity that can cause turbulence, we can have erosive loss. So we have the model to support our abrasion loss predictors. Similarly, we can test the video. We can test what we call the surface defect model, or better known as the cookie and donut model. This cookie and donut model allows us to put different recipes around the donut and test to see now if we section the interface, if there is a vein, if there is penetration, we could see that against the cookie. Okay. Let me just back up here. So we are controlling the chemistry of the alloy. This trial is for a given alloy chemistry. And the superheat temperature, the temperature that we pour from, the head pressure is controlled. We know what rho GH is for various recipes that we can have: a silica sand, a ceramic sand, a blend, etc., a coated sand, and we study it in the same mold. This is how we look at shakeout. We put a known amount of energetics, and on the design, the core print allows the sand to fall through. If it remains, we understand, again, from the retained strength, whether or not the sand binder system will lend to these productivity measures for shakeout. Okay, so here I'm showing you a cookie in the donut that shook out, one that didn't. We have this evidence. We can qualify, as I mentioned, whether the systems are urethane cold box, no bake, 3D printed, hot box. We can do that. This is the macroscope that I spoke of. This is a non-contact instrument that gives us the surface roughness, the volumetric changes for losses, and we can do this measurement at room temperature for the cookie or elevated temperature for the castings, where we could see a defect here like a vein or penetration vein, etc. we can pick up. So when we have the data from the lab test, impact strength, retained strength, abrasion, thermal distortion, etc., we also have the mold metal interface or the cookie metal interface represented here. In this case, it's iron. I'm showing you silica sand, ceramic, shell, ceramic sand. We have the surface roughness in the systems, and here is steel. This is a ceramic sand. This is a chromite sand. Not Castballs, not Castballs. This is other systems that we tested. But now I do want to show you some results relative to this qualification performance predictor of silica sand versus Castball in such an experiment. So the typical properties of the sand that I'm using, again, in this particular case, the silica sand, high levels of silica dioxide. I don't know if your silica levels are this high even in Brazil. This is probably some of the best that we have in the US, but the ceramic sand, Castballs from Brazil, high corundum materials are shown and depicted here. Okay. Now, I have collected the data on the surface roughness. The silica sand, urethane coal box, silica sand, urethane coal box, cast balls. Silica sand, round grain, shell, cast balls, shell, 3D printed silica sand, cast balls 3D printed. All the same GFN size, distribution, surface area about the same, but after these cores were made, we track the surface roughness. So we measure. As I mentioned to you, when metal touches the surface, it should get better, meaning we get a lower number. If the number goes higher, we know we have a mole-metal interfacial reaction. So look at what is happening. We perform these tests that I showed you before. We have the data. I can share this data, or the Curimbaba group, Mr. Peter can share all this data we have given him, save us some time. We have run the thermal distortion test like I showed you before, and we got all the laboratory data. Here in the silica sand, the ceramic sand, you see what's happening. But again, the foundry engineers, they like to see what is happening on a casting trial. So again, from the thermal distortion test, we want you to see, I'm pointing silica, 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 cast balls, cast balls, cast balls. Look at the thermal distortion. It's all reduced. It's all significantly lower, radially or axially. There is literally less losses relative to certain systems, but in overall distortion, the ceramic cast balls is better. But what about the casting trials? That's the qualification. The issue here, we put the cookies in the donut. In this case, we poured a grade 30 iron, a pouring temperature of 1434 from 20 centimeter head pressure. Again, to show you the model, just in case you were sleeping the first time, right? This is the idea, but there is some important information I want to show from the simulation. I want to show where the hotspot is on the cookie. This time, I want you to observe this information. So the solid fractions, as we run this, is going to be right here. Right here, it's 2 o'clock, but on the back side, it's 10 o'clock. Please remember those locations, right? And again, this is poured in a very quiescent fashion. But by the way, I want to go back here and play this again. Here is the velocities. Can't get it. Let me see if I go back. Forward. Yeah, it doesn't show. But please believe me, I will show you the data. We are less than 1.5 meters per second, so very quiescently filling, very slow, no turbulence for this iron condition. The hotspot, as I reminded you, is 2 o'clock and 10 o'clock. So let's look at the casting. Here is silica sand, defect at 10 o'clock. No defect. Look at the surface roughness, same. I don't measure this. I'm only measuring the surface roughness right there, right at this 35 millimeter diameter blue spot. But silica sand, defect 2 o'clock, right where the hotspot is. Again, cast ball, no defect, clean for shell, resin, 10 o'clock defect, like clockwork happening. And the ceramic 3D printed sand, clean. In this case, you cannot afford this defect. Why? The mold in 3D printing is more expensive than the metal. So in this case, again, regardless, 3D printing or conventional process, you do not want these defects. The reason that I'm pointing out specifically, this is a penetration. We know this is not erosion. And that's why I'm telling you it's a 2 o'clock, 10 o'clock defect. But more specifically, our Surface roughness values for the ceramic sands went down, meaning no mold-metal interaction, the smoothness is superior on those castings. And in a nutshell, that's what I wanted to show you. I'd be happy to take your questions.